Electric motors are everywhere. They drive fans, compressors, conveyors, pumps, and a host of other machines that rely on rotational force. Now, since the use of electric motors is widespread, it is essential that we have reliable methods of starting and stopping these motors and also protecting them from abnormal conditions. Over the years, a lot of methods have been developed that range from full voltage starters to reduced voltage starters, depending on budget, application, and electric motor size. The subject of this video today is one of the most widely used, one of the most reliable, and one of the simplest motor starters out there, the direct online starter. Now, the direct online should be at the fingertips of every electrician and every apprentice out there. Now, you might be learning about the direct online for the first time, or you have an idea but you haven't really quite grasped the basic concepts of a direct online starter. Well, this video is for you. And if you're an electrician who's been away from motor controls for quite a long time, consider this video a refresher. By the end of this video, you should be able to understand when to use a direct online starter. The second one, you should be able to understand the advantages and disadvantages of using a direct online starter. Third one, you should be able to draw both the control and power circuit or power schematics of the direct online using IEC 60617 symbols, and you should also be able to wire up both the control and power circuit of the direct online starter and drive a real induction motor with both circuits. You should be able to do all those things by the end of this video.
Isai mawoko oye. Isai mawoko toda kutenda mija. Isai mawoko oye. Isai mawoko toda kutenda mija. Mija oye. Mija oye. Mija we mageti. Mija we mageti. Mija oye. Mija oye. Mija we mageti. Mija we mageti.
Hi, my name is Farai and welcome to the channel Magezi 2.0, your go-to channel for everything electrical. In this video, we're going to zoom in and dive in onto the direct online motor starter, and the basics that we are going to learn in this video do not only apply to the direct online starter, but they form the building blocks of even more complex electric motor controls. So you have every reason to stick around as we learn together. Now, the first thing that we're going to do is to define what a direct online motor starter is. Now, a direct online motor starter is a full voltage starter. It applies the full voltage to the motor windings at startup, providing instant torque. For example, if a motor is connected to a 3-phase 400-volt supply, the starter will apply the full line voltage of 400 volts to the motor. Full voltage starting results in high starting currents called inrush current. This can be as much as 5 to 8 times the full load current of an induction motor. For example, a 2.2 kilowatt 3 horsepower motor with a full load current of 4.5 amps could draw up to 20 amps or even 36 amp at startup. That's a bit too much considering the motor draws less than 4.5 amps in normal operation. Now, due to the high inrush currents of direct online motor starters, the use of direct online starters is generally limited to electric motors of sizes around 7.5 horsepower up to maybe around 10 horsepower. And beyond that, you should start using other methods like reduced voltage starters, for example, the Star Delta or soft starter or variable speed drives. But you can always check your local codes for the specific limits of your country. Now let's take a look at the components that make up a non-reversing direct online motor starter. A direct online motor starter comprises a low power circuit called the control circuit and a high power circuit called the power circuit. Now imagine hooking this electric motor directly to a circuit breaker like this and using this circuit breaker for starting and stopping this electric motor. I know that even though some of you might not have experience with electric motor controls, you can almost tell that this is not quite a good idea, due to the reason that you are exposing yourself to high switching currents when you're using your circuit breaker as a switch, because this circuit breaker is not designed for starting and stopping electric motors. So you're exposing yourself to high switching currents and an arc that could cause damage to the circuit breaker itself, or even pose the risk of a fire. So that's the reason why you need an external circuit for starting and stopping an electric motor. And this external circuit is what we call the control circuit. It's a low power circuit that allows us to start and stop electric motors without exposure to the high switching currents and without exposure to the high power drawn by these electric motors. Now, one thing to note is that certain components are part of both the control and the power circuit. The power circuit consists of the incoming supply, which can be three-phase or single-phase, a circuit breaker, a contactor, an overload relay, the earth terminal, power cables, and the electric motor itself. On the other hand, the control circuit consists of the control circuit breaker or fuse, normally closed contacts on the overload relay, generally labeled 95 and 96, the emergency stop or e-stop button, the stop push button, the start push button, and normally open contacts on the contactor, usually labeled 13 and 14, which we call auxiliary contacts or auxiliary hold-in contacts. The contactor coil, generally labeled A1 and A2, and the neutral terminal depending on our choice of control voltage. Now, the purpose of this video is to take you from zero to operational, or from confusion to clarity with regards to the direct online starter. But along the way, we're gonna be repeating stuff, because I'm a firm believer that in order to drive important points home, because repetition allows us to internalize the direct online starter. Now that we have stated the components that make up both the power circuit and the control circuit of a direct online starter, let's get more in-depth and discuss the purpose of the components in the power circuit. To summarize it all, the power circuit is responsible for switching power to the motor windings and protecting the induction motor against overcurrents. The control circuit allows the safe starting and stopping of an induction motor without exposure to high power. Now, we protect electric motors from two types of overcurrents, which are short circuit currents and overload currents. So let's discuss short circuit currents first. Short circuit currents are a result of conductors of different voltages coming into contact, causing current to take a shortcut or unintended path. This results in excessive currents to flow, which can result in overheating, damage to cables and components, or even fires. In three-phase systems, short circuits can be between a phase wire and an earth, a phase wire and a grounded surface, or between two live wires of different phase angles. In a balanced three-phase system, the magnitude of each voltage, which is known as the RMS voltage of each phase, is the same. But since the three voltages are rotating at different phase angles with each other, there will be at different voltages at any given time. So if two different phases come into contact, a short circuit will occur. Now let's illustrate this point by way of an example. Let's imagine that in a three-phase system, which is three-phase 400 volts, a phased wire comes into contact with an earth wire. At the point of contact, the resistance is 0.05 ohms. In order for you to have an idea of the magnitude of short circuit currents, let's use Ohm's law to carry out a simplified calculation factoring in the resistance value only. Now, there could be many other variables in an electric motor circuit due to inductance in the electric motor windings, but let's just simplify this example and factor in the resistance value only so that we understand the magnitude of short circuit currents. Now, according to Ohm's law, voltage is equals to current times resistance. So in a three-phase system, line voltage is 400 volts in this instance. And since our line voltage is 400 volts, then our phase voltage is line voltage divided by the square root of 3, which is 400 volts divided by the square root of 3, which gives us 230 volts. So to calculate the short circuit currents, we divide voltage by resistance. So short circuit current is voltage divided by resistance, which is 230 divided by 0.05, which gives us 4,600 amps. Now imagine 4,600 amps flowing through a small electric motor like this one that is designed to only take a maximum of 1.83 amps in normal operation. That sounds extreme, right? But that is what happens during short circuit conditions. So due to the magnitude of short circuit currents, we want these fault currents to be extinguished immediately. So we rely on the circuit breaker to do just that. And the type of protection that we get from a circuit breaker is called magnetic protection, because those large fault currents activate the magnetic component of the circuit breaker, which ultimately extinguishes our short circuit current. Now let's discuss how a circuit breaker stops short circuit currents. Inside a circuit breaker is an electromagnet that activates when there is a sudden surge of current. The strong magnetic force pulls open the switch, stopping the flow of current and avoiding damage to cables and electrical equipment. The operation of a circuit breaker with regards to short circuit faults is instant. When selecting circuit breakers for motor protection, we select a type that protects our circuit against short circuits, whilst also withstanding the large startup currents without nuisance tripping. These are typically D-curve circuit breakers or C-curve circuit breakers for small motors. Now the following is a list of sources of short circuits in electric motor circuits: insulation breakdown, overheating, moisture ingress, loose or damaged connections, mechanical damage, or contaminants. After short circuits, we need to protect our electric motors from overcurrents that are associated with overloading the electric motors. Overload currents can lead to overheating of electric motor windings, which causes insulation breakdown of electric motor windings, ultimately leading to short circuits in electric motor windings. Let's define what an overload is. Overloads are fault currents that are caused by overloading the motor. They are way smaller in magnitude compared to short circuits, but they will cause overheating in the power circuit if left for prolonged periods. Protection against overload currents is called thermal protection. An overload relay protects the motor windings against overload currents. Inside, it has a bimetallic strip which relies on the thermal effect of current. When current that is more than the rated current of the electric motor flows for prolonged periods, the bimetallic strip bends, activating contacts on the control circuit that will interrupt power to the motor. The overload relay allows us to set the approximate tripping threshold for an electric motor. General circuit breakers offer thermal overload protection, but their response to small overload currents is much slower. Sources of overloads in electric motors include motors driving a load that is above their load limit, worn-out bearings on motors, gearboxes or the mechanical system, phase imbalances in electric motors, and single phasing. I hope this gives you an idea of overcurrent protection in electric motors. Now let's discuss switching in the power circuit. In an electric motor power circuit, we need methods of switching that do not expose the operator to the high switching currents which are associated with switching electric motors. So the contactor, which is activated in the control circuit, allows us to safely switch the supply to the electric motor windings. Now, a contactor is an electromagnetic switch that controls the flow of energy to the electric motor windings. When its electromagnetic coil is energized through the control circuit, it pulls the phase contacts, allowing electricity to flow to the motor windings. This mechanism allows for the switching of high-power devices using low-power circuits. Auxiliary contacts, which are part of the control circuit, also rely on the operation of a contactor. Finally, on the power circuit, let's talk about the supply cable for the electric motor and the terminal box connections on the electric motor. The cross-sectional area of the individual conductors of the supply cable should be able to handle the full load current of the electric motor. Now let's discuss the terminal box connections of the electric motor. There are two methods of connecting single-speed induction motor windings: the star or Y method and the delta method. For direct online circuits, these connections are made in the motor terminal box using the connectors supplied by the manufacturer. The choice of connections in either star or delta is based on the information supplied by the manufacturer via datasheets or more commonly on the electric motor nameplate. For example, this electric motor is connected in delta if the supply is 3-phase and 230 volts and can only be connected in star if the supply is 3-phase 400 volts. Each of the three windings of an induction motor has a beginning and an end. Most manufacturers label windings using U, V, and W, with the beginnings labeled U1, V1, and W1, and the ends labeled U2, V2, and W2. To achieve a star connection, join one end of all three windings together. Then connect the 3-phase supply to the remaining 3 ends. A delta connection is achieved by connecting all 3 windings in a loop, where the end of each winding connects to the beginning of the next, forming a triangle. However, the triangle is for representation only. You can figure out your delta loop by first making sure each winding beginning is linked to the end of the next winding. Then translate those connections onto the terminals. The 3-phase supply is then connected to all the 3 points of the conjoined windings. I hope you are still following along and you are internalizing the basic concepts of the direct online starter. And if you have any trouble understanding or grasping some of these concepts, you can always make use of the comment section, and we can discuss and see where you are facing challenges, and we can assist each other that way. Now it's time to go through all the graphic symbols that we're gonna be using for drawing the control circuit and power circuit of a direct online motor starter. Now these graphic symbols are based on the standard IEC 60617, and this is a more global standard, so I encourage you to pay attention to this standard, because a lot of equipment that you are likely to come across, whether it was manufactured in Europe or most parts of Africa, a lot of that equipment is most likely to have schematics that are based on the IEC 60617 standard. So I encourage you to pay attention to this standard. Have sound appreciation of the graphic symbols that are based on this standard. Now, in order for us to have a firm grasp of control circuits, we need to master the operation of normally open contacts and normally closed contacts. So before we go through all these different components that make up both the control and power circuit, we're going to dive into how normally open and normally closed contacts work. Now, let's go through normally open contacts first. Normally open contacts are open in the default state. They close when the device is activated, allowing the flow of current. They are labeled with any combination of numbers where the least significant numbers are 3 and 4. For example, they can be labeled 3 and 4, 13 and 14, 53 and 54, and so on, as long as the least significant combination of numbers is 3 and 4. The only normally open contacts which are labeled differently are the ones that you find on traditional overloads, which are labeled 97 and 98. Start push buttons which you use in a direct online starter are normally open contacts. And then normally closed contacts are closed in the default state. They open when the device is activated, interrupting the flow of current. They are labeled with any combination of numbers where the least significant numbers are 1 and 2. For example, they could be labeled 1 and 2, or 11 and 12, or 21 and 22, and so on, as long as the last number is 1 and 2. Now, the only normally closed contacts which are labeled differently are the ones on a traditional overload, which are labeled 95 and 96. The stop button and the emergency stop buttons that we use in direct online circuits are normally closed contacts. In a simple non-reversing direct online starter, devices with normally closed contacts are wired in series with the control circuit. Now, when it comes to electric motor control circuits, we generally have two types of contacts as well, which are momentary contacts and latching contacts. A momentary contact is an electrical contact that remains in its activated position, whether open or closed, only while it is pressed or held. Once released, it returns to its original state. Examples include start and stop push buttons, such as the ones used in control circuits. A latching contact is an electrical contact that maintains its position, open or closed, after being activated until manually reset or switched again. Most e-stop buttons are latching contacts, requiring a twist or pull action to release them. Now that we've discussed the basic building blocks of both the power circuits and control circuits, let's look at all the symbols that make up both the control and the power circuits. Let's keep in mind the components that appear in both control and power circuits. For short circuit protection in the power circuit, we rely on circuit breakers. A separate single pole or double pole breaker may also be used for protecting the control circuit. A control circuit breaker helps during quick troubleshooting when there is a need to isolate each circuit without disconnecting any wires. Now, so that's the general symbol for a circuit breaker, and this one is a single pole breaker. But if you want to add more detail, you can draw this symbol here. And this is what you are more likely to come across in schematics. So this part here indicates thermal protection, and this part with these curves here indicate magnetic protection. So a general circuit breaker normally has thermal protection and magnetic protection. But in a motor control circuit, we are installing those circuit breakers mainly for the purpose of protecting electric motors against short circuits. And we put a dotted line here on all the 3 poles. This just tells you that these 3 poles are mechanically linked, just like on this circuit breaker here. Because what could happen is a short circuit could occur in one phase. If if they were not mechanically linked like this, only that phase would trip. But since we've linked them like this, if a short circuit occurs in just one phase of this circuit breaker, then that phase trips is going to force all the other two phases to trip as well. Now, the next component in our control circuit is a contactor. Now, the contactor is part of both the power and control circuit. The contacts on the power circuit are designed to handle the large switching currents. Always check manufacturer specifications to make sure your selected contactor can handle the inrush currents of your electric motor. The normally open auxiliary contacts are either built-in or clip-on. So this is a contactor. So this contactor that I have here already has built-in contacts that we need for our control circuit. So these are built in, which is 13 and 14. They are built onto the contactor here, as you can see, 13 and 14. But if this contactor didn't come with auxiliary contacts built onto the contactor, or we needed additional maybe normally closed or normally open contacts for interlocking with other equipment, we could use external or clip-on auxiliary contacts like this one. So this one has got two sets of normally open contacts which are on the outside, and two sets of normally closed contacts which are on the inside. So this one is an auxiliary contact block that we can use for other interlocking purposes. And what we simply do is to clip it on to the contactor like this. The normally open auxiliary contacts are also called auxiliary hold-in contacts, as they hold the contactor coil in place. The contactor coil is part of the control circuit. Contactor coil voltages or control voltages are selected based on application and availability of voltages. Common coil voltages include 48 volts AC, 110 volts AC, or 220 volts AC. This is our contactor. So this is the part that belongs to the power circuit. This is the part that switches on our supply to our electric motor windings. And the power contacts and the control contacts, they are all switched on by the contactor coil. So when the electromagnetic coil on the contactor A1 and A2, which is A1 and A2 here, so when it's activated, it closes these contacts on the power circuit side of the contactor, which is 1, 2, 3, 4, and 5, and 6. So these are the three poles on the power circuit side of the contactor. And the coil also operates the auxiliary contacts, which can be built in or they can be clip-on onto the contactor. So normally open contacts that we have here are 13 and 14, and the normally closed contacts that we have here are 21 and 22. And remember what we mentioned about normally open contacts. We said normally open contacts, they always come in combination of numbers that end in 3 and 4. It could be 3 and 4, it could be 13 and 14, 23 and 24, or 53 and 54, as long as the last number or the least significant numbers are 3 and 4. Then that tells you that it's a normally open contact. And on normally closed contacts, as long as the least significant number is 1 and 2, that tells you that it's a normally closed contact. So normally closed contacts always end in 1 and 2. They could be 1, 2, they could be 21, 22, or 41, 42, as long as the least significant numbers are 1 and 2. So this is the symbol for a contactor. So this part belongs to the power circuit and this part belongs to the control circuit. But for a simple direct online starter that we're going to do today for this activity, we don't necessarily require the normally closed contact. We only require on the control side, we only require the normally open contact, which is 13 and 14, and the contactor coil. So the contactor coil and 13 and 14 here, these are part of the control circuit. And this control circuit is operating the contactor coil, which in turn operates the power contacts on the contactor itself. I know we are going to gain more clarity as we start to utilize these symbols when we are drawing the actual circuit. And then the next component that we are going to discuss here is the overload relay. Just like the contactor, the overload relay is part of both the power circuit and the control circuit. So the symbol for the overload relay is like this. On the overload relay, there's a normally open contact, which is 97 and 98, and a normally closed contact 95 and 96. For this control circuit or for this exercise, we are only interested in the normally closed contact, which is 95 and 96. So for the symbol here, we're not going to bother ourselves by drawing the normally open contact because we don't need it for this exercise. We just need the normally closed contact. So this is the control circuit symbol for the overload relay. I know some of you might have seen different symbols for overload relays, but this is the one that you're gonna be using. So you can just browse on the internet to check for the other symbols or graphic symbols that are used for representing the overload relay, but this is the one that you're gonna be using. And if you use this one, I say that you are pretty much covered, pretty much fine. As we mentioned earlier on when we discussed normal open and normally closed contact, we say that an overload relay is an exception which doesn't follow the common labeling rules that we use for normal open and normally closed contact. So for the normally closed contact on an overload relay, it's labeled 95 and 96. It doesn't follow the rule of 1 and 2 or of numbers that end in 1 and 2. So always bear in mind that for this type of overload relay, the old school type of overload relay, you're more likely to find the normally closed contact labeled as 95 and 96, just like what we've done here. So this is the power circuit symbol for an overload relay, and this is the control circuit symbol for an overload relay. Now let's move on to the next component. Now the next component as we round up the power circuit is the electric motor. Now, electric motor is quite simple, but we can as well just draw the symbol to make sure that we are on the same page. So electric motor is simply a circle like this. So if it's a three-phase motor, we draw our 3 wires going to the electric motor, and normally we draw them like this. Some will write M or 3-phase motor, and you might decide to show the earth connection here. And sometimes what others will also do, they will show the terminal connections as well, which is normally U, V, and W. And as we proceed, you realize that when you do star delta circuits, you are going to require both ends of your windings. So you're going to require 6 connections to electric motor. But for a simple electric motor connection that is being driven by a direct online circuit or by VSD, you just need to connect to 3 points on the electric motor. So this tells you that it's a 3-phase electric motor. If it was a single-phase electric motor, normally we would just have 2 points where we are going to connect our supply, which is the live and the neutral. All right, now that we've discussed about the electric motor, let's go to the next component, which is the emergency stop button. Now, the emergency stop button belongs to the control circuit only. It's not part of the power circuit, but it's just part of the control circuit. Emergency stop buttons in direct online circuit we use the normally closed contact on emergency stop button. Now that doesn't mean that that's the only contact that you can use for emergency stop buttons, but for this purpose we are going to be using the normally closed contact, and it's the most common contact that we use on emergency stop button. So one that normally closed contact on emergency stop button to allow the flow of current during normal operation and only interrupt the flow of current during an emergency. So the basic contact on an emergency stop button is a normally closed contact, but now we're going to require something that is going to tell us that it's an emergency stop button. So the first thing we do is to label our contacts here 1 and 2, but that all depends. Like this, the one that I have here is labeled 11 and 12, but most emergency stop buttons have got contacts labeled 1 and 2, but we know that any number that ends in 1 and 2 is a normally closed contact, and it's perfectly fine for our needs. So the common emergency stop button is what we call a mushroom head, like this one, because it looks like a mushroom head. A mushroom head e-stop, we draw it like this. So this is the graphic symbol for a mushroom head e-stop, and then this part here tells us that it's an e-stop. And for this one, okay, so this part tells you that it's a latching contact. This one tells us that it's a latching contact. And this type of e-stop that I have here, when you press it, it latches, and in order for you to release it, you have to twist it to release. So this one is a twist to release e-stop. We have different types of e-stop. Some of them are pull to release. You know, you push them in, and then to release, you have to simply pull them out. But this one is a twist to release. So the symbol for the twist to release e-stop is like this one. So this is our e-stop. It's a normally closed contact. So this is the symbol that we're going to be using when we're drawing our schematics. The next in line is the stop push button. And as well, just like the emergency stop button, the stop push button for a direct online starter, a simple direct online starter, we rely on the normally closed contact. We draw a normally closed contact like this one. Could be 1 and 2, and mostly they are labeled 1 and 2. Now we need something that tells us that it's a push button. So for a push button, this is the general symbol for a push button. Draw this one, and you draw a dotted line connecting to our contact here. So it just tells us that this push button is mechanically linked to this contact. So this push button is the one that's operating this contact. Now, when you draw it like this, it tells us that it's a momentary contact. It doesn't latch. So which means that for a stop push button, it only remains in the open position as long as you keep your finger pressed on that button. But as soon as you release your finger from the push button, then this contact is going to go back to its default state, which is the closed position. So this one is your stop push button, like this one. And the last push button in our direct online starter is the start push button. The start push button, just like the stop push button, is also a momentary contact push button, and it's a normally open contact. So one thing you always have to remember is when you are drawing symbols according to the IEC 60617 standard, your normally open contacts will always be facing to your left, and your normally closed contacts will always be facing to your right. So this is the general symbol for a normally open contact, and it's labeled 3 and 4 most of the time, or any combination of numbers ending with 3 and 4. So this is a simple normally open contact. Now we need something that tells us that it's a push button. So we draw our general symbol for a push button, and the dotted line linked to our contact here. So this one tells us that this push button is mechanically linked to this contact. So this push button is the one that is operating this contact. So this is your start push button, and it's a momentary contact, which means if we press it, it only remains engaged or in the closed position as long as we maintain our finger on that push button. But as soon as we release our finger from the push button, then this contact goes back to its default state, which is the normally open position. Now let's quickly discuss the fail-safe mechanism of a simple direct online starter circuit. So if this circuit is stopped by an overload or by an emergency stop, it will not restart itself even after the emergency stop button is reset, or even after the overload is reset. So this is an important safety mechanism for this type of direct online starter circuit. Now, before we draw and wire up the direct online control and power circuits, let's quickly go over the advantages and disadvantages of direct online motor starters. So we're going to start with the advantages. So the first advantage is that a direct online motor starter is simple and inexpensive due to fewer components. The second one is direct online motor starters are reliable due to less components, and less components means less parts that are likely to fail and less time that is spent on troubleshooting and maintenance. And the third advantage is that the direct online motor starter offers quick startup. Now, the quick startup is due to the full voltage starting of the direct online motor starter, and having full voltage startup allows for immediate torque on the motor shaft. Now, let's discuss the disadvantages of the direct online motor starter. The first one, obviously, is the high inrush currents, which cause significant voltage drops on the power supply with the potential to cause damage to electrical equipment. The second disadvantage is the limited motor size. And the third one is mechanical stress. So starting your electric motor at full torque and stopping abruptly without decelerating gradually causes bearings to wear out faster. Now it's time to get practical. Let's draw both the control circuit and the power circuit of a direct online motor starter, and after that we proceed to do the wiring of both the control circuit and the power circuit and run this three-phase induction motor. We're gonna do it today, and by the end of this video you should also be able to do the same, draw the control circuit and the power circuit of a direct online motor starter and run a real induction motor by yourself. So drawing the control circuit should be easy. So the first thing is in our control circuit is our control circuit breaker. So we just use the general symbol, which is quite simple. And then from the control circuit breaker, you go to your 95 and 96 on your overload. So my control circuit breaker here is a 6 amp single pole breaker. I'll just label it SPB, and then I'll go to my overload, which is 95 and 96. And then from the overload, let's go to the emergency stop, which is labeled 1 and 2, mushroom head, latching, contact, twist to release. So this is your e-stop. From the e-stop, we go to your stop button. It's got a normally closed contact at the back, 1 and 2. From your stop push button, we go on to the start push button, which is labeled 3 and 4. Now the start push button is connected in parallel with your auxiliary hold in, and our auxiliary hold in is labeled 13 and 14. But we shouldn't be memorizing those numbers. What we should just know is it should be a normally open contact. So if we are using this auxiliary contact block, there's no 13 and 14, but can we say we don't have a normally open contact Of course, we have one, but the one, if you're going to be using this auxiliary contact block, you're going to be utilizing 53 or 54 or 83 and 84, as long as the least significant numbers are 3 and 4. So we're going to be using the auxiliary contacts that are built onto this contactor. So they are labeled 13 and 14. And next up is the contactor coil, which is A1 and A2. Now, I know that a lot of you have got different graphic symbols that you use for the contactor block. Some, they put a diagonal line inside here. Whatever you do, it doesn't matter. And some, they put do this, whatever, as long as there's some form of uniformity in the symbols that you use. But for me, I just prefer to leave it blank because it saves time, you know, not too many lines drawn. So this is our contactor. So here I just put my line at the top, and I just labeled it live. If you are doing this for a real circuit, it might be worth it to actually indicate on which phase that you are getting your control voltage from, because if it's a three-phase system, then you want to know from which phase are you taking your control, from L1, or are you taking it from L2 or L3. And I know that there are different colors for different countries. Some countries, they use red, white, and blue. Some, they use red, yellow, and blue. So are you getting your control from the red phase, or are you getting it from the yellow phase, or are you getting it from the blue phase? Always indicate. But here I just put live at the top here. So it should be sufficient for our practice. So I have the control voltage supplied separately from the three-phase supply that's going to run this motor, because where I am here, I don't have a three-phase supply. So I'm going to use a variable speed drive to generate the three-phase that I'm going to require to run this electric motor. So I cannot use one of the phases from that variable speed drive. Okay, so basically, this is the control circuit. Okay, one other thing that we should always remember is contactors are generally labeled KM. Some just label them K, but for a lot of people, the standard for K is reserved for a general relay. But then if you see KM, because K stands for contactor, M stands for motor. So if it's KM, it tells you that it's a contactor that is being used to switch the power to an electric motor. The reason why I put KM on 13 and 14 is I'm just indicating that KM, this contactor coil, is also the one that is going to operate this contact as well. Now let's draw the power circuit. So you're gonna have obviously your three-phase supply here, L1, L2, and L3, and then I'm just gonna draw the general symbol for a circuit breaker. I'm not going to do anything fancy here. So what I have here is a C-type circuit breaker. It's okay for a small motor like this one, but generally you should use a D-type circuit breaker, as we've mentioned before, because a D-type circuit breaker allows for the high inrush currents. So this one is 2 amp triple pole breaker. And then we go on to our contactor here. Remember, they switch at the same time. So this is the same KM. So if you've got several contactors in your circuit, so you're gonna need a way of labeling them, of identifying those contactors. So you're gonna label them KM1, KM2, and so forth, so that someone who looks at your circuit is able to make sense of your schematic. So here there's just one contactor, so that's the reason why I just labeled it KM. So this is the same contactor coil that is appearing in different places, but it's the same contactor coil. What this just means is that this is the same KM which is operating this contact that are switching the main supply to our electric motor. It's also the same contact which is switching on this 13 and 14 on the auxiliary contacts. So from the contactor, we go to our overload relay. And from our overload relay, we go to our electric motor, which is a three-phase motor, and here's F. So this is basically it. And for more detailed schematics, sometimes they will indicate the range of tripping currents of your overload relay. Like this one that I have here is it ranges from 1.6 amps to 2.5. It's your choice if you want to include this detail. So this is the basic power circuit of a direct online starter and the basic control circuit. So these are the circuits that we're gonna wire up to run our electric motor. So what I'm gonna do here is to just explain briefly how the control circuit works. After you've wired up your circuit, obviously you switch on your control circuit breaker. So when you press the start push button here, in that moment this contact is going to close and current is going to flow from your supply through the normally closed contacts on your overload relay. They are closed, so they will allow current to pass through. The stop push button as well is normally closed, so it will allow current to flow through its contacts. And as this current flows through the start push button, in that moment, as our finger is pressed on this button, it will power up the contactor coil at A1 here, and A1 and A2, it doesn't matter where you connect your live or neutral, current will flow through and then power up this contactor. So as soon as this contactor is powered up, it engages, and as soon as it engages, it closes this contact here, 13 and 14. And when it closes this 13 and 14, it creates another parallel path of current. So when you release your finger from the start push button, what's going to happen is that this contact is going to open on the start push button. When it opens, what's going to happen is our contactor will remain engaged. Why? Because we've already created another parallel path. So this 13 and 14 will remain engaged, and that's why we call it the hold in or the auxiliary hold in, because it will maintain a path for the flow of current to our contactor coil as long as we keep that circuit switched on. So it will only stop if it's interrupted, maybe by by pressing the stop button in normal operation, or by pressing an e-stop in an emergency situation, or if the motor trips due to an overload. Three-phase circuit breaker will be switched on here, and then when this contactor engages, it means that it closes these contacts and current will flow to our motor windings. We'll switch on our supply voltage, current flowing to our motor windings, and our motor starts to rotate. So an important ability that you can develop that can tremendously help you when you are working with control circuit, especially when you start designing your own circuits, you should have the ability to study your circuit on paper and establish that your circuit works before you even wire it up. What we're going to do is we're going to wire up the control circuit. So before we do that, we're just going to go through the control circuit and make sure that we've done everything right. So we're just going to establish that our circuit works before we wire it up. We're going to start with the control circuit. So the first connection is going to the top of the control circuit breaker, and this is coming from one of the phases on our main supply. So we draw from one of the phases to the top of our control circuit breaker, and then we get a connection from the bottom of our control circuit breaker to 95 on our overload relay. So we draw a connection from 96 on the overload relay to 1 on the e-stop button, and then from 2 on the e-stop button we go to 1 on the stop button, and then from 2 on the stop button we go to 3 on the start button. So 3 on the start button is the same connection with 13 on the auxiliary contact. So we connect a cable from 3 which goes back to our contactor, and we connect it to 13, And then from the bottom of our start button at 4, we connect another cable that is long that goes back to our contactor, and we connect it to 14. So this point here, 14, is also the same point with the contactor coil, which can be A1 or A2. So I would say just connect it to the one that's most convenient. 14, we connect it to the contactor coil, and the remaining point on the contactor coil, we connect it to our neutral, and that's it for our control circuit. And then on the power circuit side, it's pretty straightforward. All the power circuit components are connected in series with our electric motor, and it shouldn't be a difficult thing for this non-reversing direct online starter. So we just connect our supply to the top of our circuit breaker, and then from the bottom of our power circuit breaker, we'll take our 3 conductors and then we connect them to the top of our switching contactor. At the bottom of our contactor is linked with our overload relay, and then we don't need to link it with any cables there. So we should always select a contactor relay that is compatible with the type of contactor that we are using to make sure that we don't create loose connections. And then from the bottom of our overload relay, then we connect our supply cable that goes straight to our electric motor. For our electric motor on this exercise, remember, we connect it according to the manufacturer specifications, depending on the supply voltage that you have. Tighten.
Mageti moto, yeah, hey, Mageti moto, yeah, hey, Mageti moto, yeah, hey, Mageti moto, yeah, hey. Isai mawoko, oye. Isai mawoko, toda kutenda misha. Isai mawoko, oye. Toda kutenda misha, oye. Misha, oye. Misha, we mageti. Misha, we mageti.
Yeah, so that's it. Now I've finished doing the control circuit and the power circuit, and that tells you that the direct online motor starter, once you get it going, it doesn't take you that much time to install. The best thing to do is to always go through your connections once again after you've completed doing your wiring. So I'm just going to quickly trace through my control wiring just to make sure that I've done the right thing. So my first connection here is coming from my supply, which is this is the red, from the red terminal here. It's going to the top of my control breaker. Then it goes into 95, just like on our circuit diagram here. Then from 96, it goes to 1 on our e-stop here, just like here. And then my e-stop is looped to my stop button, to 1 on my stop button. And then from my stop button, I go to the start button. So to the top of the start button, it's linked here. Then I have a long lead which connects 3 to 13. So from 3 on my start button, it goes straight to 13 here on my auxiliary contact. And remember, I didn't have to use this clip-on auxiliary contact like this because my contactor already has auxiliary contacts here. So I just need one set of normal open contacts for this simple direct online starter. So from start here, I have this long wire going to 13 here. So I've tucked it underneath over there to reduce the spaghetti here. And then from the bottom of my start push button, on 4 on my push button, I've another wire that is going to 14 on my auxiliary contact. So this is the one that's going to 14, and 14 here on my auxiliary contact. This is the same point with A1 on my contactor. So I've conveniently connected to A2 because A1 or A2 doesn't make any difference. You just connect to which one is convenient or which one is closer to 14. So I've connected here to one terminal of the contactor coil. So this connection is already there. So now I'm left with the other connection that goes to neutral. I've taken it off A1, and then it goes to my neutral connection, which is on the blue terminal here. So basically, everything is pretty much covered up. And then the power circuit is pretty much straightforward. I have my supply coming in here, red phase, white phase, and blue phase. And then I have this same supply going to the top of my contactor. Now I need to connect my electric motor to the bottom of my overload relay, and then I'll be done with the power circuit. And also make sure that I properly connect this electric motor to earth as well. Now we're not going to go through the terminal connections in this electric motor. We'll do that in subsequent videos, but if you need to do connections, just follow the instructions that we briefly went through for the delta or for the star connection when you are connecting your electric motor. So this motor is already, so this cable is already connected to the motor terminals. So I'll simply connect it to the bottom of my overload relay here, and also make sure that it's safely connected to earth as well. So now is the time of reckoning. It's time to test if our control circuit and our power circuit works. So we're gonna start by testing our control circuit, and then when we are satisfied that it's working properly, then we'll proceed to switch on our power supply and test the power circuit as well. So yep, see, it's working. I can stop it, start, and then I can press my e-stop, and then when I release my e-stop, my circuit doesn't engage automatically. I have to press the start in order to start the circuit again. So that's an assurance that my motor, my electric motor, is not going to restart on its own. All right, now I'm going to switch on my power supply, my 3-phase power, so that we can run this electric motor and see if we've done the correct thing. Yeah, that if you can hear a little fan running, that's from my variable speed drive, which is providing us with the 3-phase power. So let's start our electric motor and see if we've done the right thing. See, it's running. So bingo, it's going well. And now we can simulate a trip on the overload and see if it stops. See? Now we have to reset the overload. Now let's start it again. So we've reset the overload, but the motor doesn't restart on its own. So we've done the right thing. Started it again. And our stop works. Now let's run it for the last time. And let's check our e-stop if it works. All right. So we've done it. Now I can safely say that we've done it. We've successfully drawn a control and power circuit for a direct online starter, and we've wired it up, and we're able to run a 3-phase electric motor from this circuit. And I hope that you too have learned the basics of the direct online motor starter, and you'll be able to essentially do the same thing that we've done here. You'll be able to draw the control circuit, draw the power circuit, and wire it up to run a real induction motor. And to those guys, the electricians who've been away from motor controls for quite some time, I hope that this video has provided you with that little refresher, and you'll be able to confidently go back and work on electric motor controls, find a way to get components, and always practice all these circuits so that you start with this direct online starter, know it like the back of your hand, and learn how to wire it up quickly, how to troubleshoot, how to maintain it, and then just build it up from there. And then obviously from here we'll have to do the direct online forward and reverse circuits. But before we do that, in our next video we're going to do the direct online starter for single phase motors. Yes, single phase motors. A lot of you think that single phase motors just come with these special control boxes, but you can pretty much run a single phase motor with a direct online circuit, just like what we've done on a 3-phase motor. But there are certain things that you need to pay attention to, and that's what we're going to address in our next video. And the video after that one, we should be able to do a conversion, convert this 3-phase electric motor, convert it to run like a single phase motor, and run it with a single phase supply. So those are some of the activities that we'll be doing in subsequent videos. So you have every reason to stick around as we learn and grow together. Tonana.
Misha, misha, woye. Misha, misha, woye. Misha, misha, we mageti. Misha, we mageti. Misha, misha, woye. Misha, misha, woye. Misha, misha, we mageti. Misha, we mageti. Isai mawoko toda kutenda misha.